For over a century, some mathematical problems have been called impossible. The brightest minds threw everything they had at these equations and came up empty-handed. One problem was so notorious it carried a £1 million prize just for solving it. Then something extraordinary happened. In September 2025, an artificial intelligence did what no human ever could. It cracked open a mathematical mystery that had stumped researchers for 150 years, revealing entirely new solutions that could transform everything from weather forecasting to aircraft design. The story begins with what mathematicians call the Navier-Stokes equations. These mathematical formulas describe how fluids move through space. When you watch smoke rising from a candle or feel turbulence on a flight, you're witnessing these equations in action. The Navier-Stokes equations govern air flowing over an aircraft wing, water rushing through pipes, and storm systems forming in our atmosphere. They're fundamental to understanding our physical world. Yet despite their importance, these equations harbor some of the deepest mathematical mysteries ever encountered. The problem lies in something called singularities, or blow-ups, as researchers often call them. These are mathematical scenarios where values like pressure or velocity shoot to infinity. Whilst you'd never see infinite pressure in real life, these theoretical extremes help scientists understand where the equations start to break down. Finding these singularities in the three-dimensional Navier-Stokes system has been one of the 7 Millennium Prize problems. The Clay Mathematics Institute offers $1 million for solving each of these notorious challenges. They represent the hardest unsolved problems in mathematics, and only one has ever been cracked. But DeepMind, Google's AI research division, took a completely fresh approach. Instead of traditional mathematical methods, they turned to something called physics-informed neural networks, or PINs for short. Unlike ordinary neural networks that learn from massive datasets, PINs are trained directly on the equations themselves. The network's output is constantly checked against what physics expects to happen. By minimizing the gap between its predictions and the actual mathematical requirements, the AI learns to follow physical laws. The breakthrough came when these AI systems discovered entirely new families of singularities. These weren't just random computer glitches, but mathematically rigorous solutions that human experts from New York University, Stanford, and Brown University later verified as correct. One of the most fascinating discoveries was a clear pattern in how these blow-ups behave. The research team found that as singularities became more unstable, there was a surprisingly predictable relationship between the speed of the blow-up and the number of ways the solution could deviate. This pattern appeared across multiple fluid equations, suggesting there might be a whole landscape of undiscovered singularities waiting to be found. It's like finding a map to mathematical territories that were previously invisible. The level of precision achieved is mind-boggling. According to the research team, their largest errors were equivalent to predicting Earth's diameter and being off by just a few centimeters. That's the kind of accuracy needed to capture these delicate mathematical phenomena. Yongji Wang, the study's lead author from New York University, explained how they transformed PINs from simple problem-solving tools into discovery engines. By embedding mathematical insights directly into the neural network training, they could find solutions that had eluded conventional methods for generations. The visual representations are equally striking. The researchers created detailed maps showing how these singularities evolve, tracking vorticity fields that measure how much fluid spins at every point. You can literally watch these unstable mathematical structures develop and change over time. These discoveries aren't just academic curiosities. Better understanding of fluid dynamics could lead to more fuel-efficient aircraft, more accurate weather predictions, and deeper insights into everything from planetary formation to blood flow through arteries. In meteorology, these advances could sharpen hurricane forecasts and improve climate models. In aerospace engineering, they offer paths to reduce turbulence and cut fuel consumption. The implications stretch from everyday engineering problems to fundamental questions about how our universe works. But this breakthrough represents something even more profound. We're witnessing the emergence of computer-assisted mathematics, where AI systems navigate mathematical landscapes that humans couldn't realistically explore alone. The traditional approach to mathematical discovery has always relied on human ingenuity and logical reasoning, with computers perhaps helping with calculations. Now we're entering an era where AI can flag potential solutions and guide researchers toward discoveries they might never have found otherwise. This collaboration between human mathematicians and artificial intelligence is being hailed as a new paradigm for scientific research. The AI doesn't replace human expertise, but amplifies it, pointing toward solutions that experts can then rigorously verify. The unstable singularities discovered by DeepMind require incredibly precise conditions to exist. They're mathematically fragile, but they reveal deep truths about the structure of the equations themselves. Mathematicians have long suspected that stable singularities simply don't exist in these boundary-free three-dimensional systems. Finding unstable ones is therefore a major breakthrough. These delicate mathematical structures provide windows into the fundamental nature of fluid dynamics and might hold keys to solving the complete Navier-Stokes problem. The research methodology itself represents an innovation. Rather than brute-forcing simulations with supercomputers, the team used graph neural networks combined with physics-informed approaches. They achieved what researchers called near-machine precision, using advanced training techniques like second-order optimizers. This work was truly collaborative, involving not just AI researchers but mathematicians and geophysicists from leading institutions. The interdisciplinary approach was crucial for ensuring the discoveries were mathematically sound rather than just computational artifacts. The implications extend far beyond fluid dynamics. This demonstrates AI stepping into fundamental science, tackling problems that resisted centuries of human effort. It shows how machine learning can expand what research itself can achieve. Of course, breakthroughs like this also raise questions about the future of scientific discovery. When an AI starts solving problems once thought impossible, it highlights both the incredible potential and the need for responsible development of these technologies. Some voices in the technology world have already expressed concerns about ensuring AI development remains beneficial and controllable. The same power that unlocks scientific frontiers could potentially be misused if not properly managed. But for now, the focus remains on what's been accomplished. A century-old mystery in mathematics has been cracked open, revealing new mathematical territories that were previously invisible. Problems once called impossible have become playgrounds for machine learning. This feels like the beginning of a new chapter in human knowledge. We're seeing AI systems that don't just process information faster than humans, but actually discover new mathematical truths that expand our understanding of the universe. The Navier-Stokes equations still hold many secrets, but thanks to this AI breakthrough, we're closer than ever to unlocking them. And that's not just an academic achievement, it's a step towards solving some of the most fundamental questions about how our physical world actually works.